session is going to be Amar Hadzihasanovic, who, as you may have heard last night, has won the award for the best student paper. So I'd like to Amar to tell us all about GHZ and W states.
Oh, hi everyone. I'd just like to thank the program committee for this award, which apparently everybody else here knew about except me, because I'm sloppy in reading my emails. So anyway, it's the year 2065. There are 3 children playing with their quantum secret sharing devices, which everybody of course has in the future. And at some point one of the 3 children gets annoyed with the other 2. And so just say, I don't really care about your stupid quantum secrets. So he just sets his device to basically to reject any incoming connection. So what happens to the other 2? It turns out that if the device is sending to them GHZ states, then the other 2 children lose their connection and great sadness ensues. However, if they were getting W states, actually the 2 others still maintain a connection, so they are able to generate a secret key to read each other's secret diary, and they become best friends. So it turns out that just by tinkering with their devices, these users, whichever connected state they were sharing at the beginning, they could turn either into the GHZ state or into the W state. So these 2 are kind of complete representative of classes of tripartite qubit states under local invertible operations, what is called the lock classification. However, for higher numbers of qubits, it is not really, this classification becomes more complicated because the number of classes explodes. But more in general, one would like to have a kind of operational understanding of different quantum states with regards to these kinds of scenarios, which right now we are lacking. So what could be the categorical quantum mechanics approach to this problem? Well, by playing with these diagrams in complex closed categories, something that you start doing quite quickly is just forget about the distinction between inputs and outputs of a map. So in the end, it's only the arity of a certain map which counts by map state duality. So we have these 2 tripartite states, and they can be equivalently seen as binary operations. So in a paper of 5 years ago, Bob and Alex showed that actually to GHZ and W states, one can associate particular kinds of binary operations. They define commutative Frobenius algebras. These 2 Frobenius algebras have a specific different property, which turns out to be a kind of complete Zlock invariant for 3 qubits. But once we have Frobenius algebras, we also have the diagrammatic calculus for them. We have string diagrams, and once we have string diagrams, we really want to compose them, put them together. So the idea emerged of using GHZ and W gates as building blocks for states of a higher number of qubit, and perhaps try to use this as a way to find a representation of different classes of entanglement. So when I started working with this, the goal was to find first exactly what one can build using these 2 building blocks, and possibly other things which fit well together with them, and then find a complete set of graphical axioms which would axiomatize, which would decide the theory of identity for whatever can be built with them. And 2 things that I really cared about in looking for this axiomatization, and which are actually met by the basic version of the ZX calculus, and which I wanted to have in this calculus as well. First, when using string diagrams, it is easy to get tricked into thinking that certain operations can be performed on diagrams, whilst they can't. So I really wanted to have a graphical calculus which faithfully represents symmetries. So basically, if it looks like I can interchange 2 wires or do something like that, then I can. And the second thing is that, well, the choice of what constitutes a good axiom is pretty much a matter of aesthetics. I just thought I would rather settle for axioms which would look familiar to algebraists or topologists rather than defining weird ad hoc structures. So the result of this research is called the ZW calculus. It turns out that by using GHZ and W gates, plus actually, in the calculus we also have binary gates which correspond to the Z and the X Pauli gates. One is able to describe this category, the category of free abelian groups on a certain number of generators, which are generated by the free abelian group on 2 generators under tensoring. Well, more informally, this is just qubits with integer coefficients, because abelian groups is the same as Z modules. One can embed integers in complex numbers, so embed Z modules in complex Hilbert spaces. So every map of qubits, which can be expressed only with integer coefficients, is represented by this. And I have a complete set of axioms which I'm going to present to you. This is actually slightly different from the one which you will find in the paper, but I hope it will expose more clearly how I think this kind of theory comes together in different layers, in different modules, if you want. So, in the beginning we only have wires. There's a lot of space to move them around. One can bend them in one direction, one can bend them in the other direction. They can pass over each other, and since there's so much space, one can move one strand below the other, so this is actually symmetric braiding. And these three things together satisfy what you would expect them to satisfy, so these exact equations and the symmetric braiding versions of the Reidemeister moves. But these wires can also do this other thing, which I call the crossing. So basically, when two wires cross each other, it's as if they are kind of more tightly braided, so they're flattened against each other, so there's less space. And crossing wires together with a cap, they do satisfy the second and third Reidemeister rules. But the first one is to be replaced by this one. So two kind of self-linkings equal to identity. And in topology, things that satisfy a rule of this kind are the so-called framed links with the blackboard framing, which is basically ribbons which are constrained to stay flattened on a flat surface, but with symmetric braiding. So we still can move one strand below the other, we just can't unwrap this kind of self-loop. I mean, we can't unwrap just one, we need another one. But so far the theory is not very expressive. Basically the only non-trivial thing that can happen is this self-linking thing. So we add other generators. And we add the W algebra, which I mentioned earlier. And as you can see in the graphical calculus, this is actually a compound gate. It comes as a ternary black vertex followed by a binary black vertex. And this has to do with these considerations about not suggesting symmetries that are not there. Here, so you can interchange these two wires. You can't interchange the output wire with the other two. But for now, you should think of these as a kind of unbreakable molecule of gates. So what does it satisfy? It satisfies the monoid equation. It is monoid with monoidal unit given by the multiplication with the two inputs plugged into each other. And this monoid works really well with the crossing, actually. It seems to live in a world of crossing. So it is crossing commutative. The crossing is natural for this multiplication, so it passes through with no problems.
If you've got a symmetric monoidal category, you don't have to say all your generators that the crossing is natural for it. It has.
And in this case, just the crossing, it will not be natural for everything. So far, it's still a kind of symmetric monoidal width. But it's like having two different braidings, which only one will turn out to be natural for everything. But most importantly, if you flip the monoid around in order to get a comonoid, this turns out to be a bialgebra with its flipped around version. There's another axiom which is satisfied by these. So if you have two self-linkings coming in, you get one out. So this kind of thing would be a homomorphism for this monoid.
There's not a difference between a leftward pointing twist.
No, there's no difference. It's like, yeah, you can just.
Was that in the axioms or is that a consequence of the axioms?
It's kind of it's a consequence of everything being natural for the symmetric braiding, for the real braiding in a sense. And actually, if we wanted to stop here, we would have to add this other axiom, making bialgebra an actual Hopf algebra, with antipathy given exactly by the self-linking. But actually, this would be provable once we move on. And already with this limited number of generators, this is already quite expressive because we can build this triangle of W gates, which semantically corresponds to the ternary red gate from the ZX calculus. So algebraically, this is kind of operation which acts as Z2 addition on the computational basis. And this is actually Slack equivalent to GHZ. So now one can take this kind of algebraic operation and make a kind of a product of a number of them by making the different ones cross each other. And if one takes P of these and Q of these, and the second Q are kind of the multiplication is preceded by another crossing, one actually gets something which, when interpreted in real vector spaces, so yeah, you interpret it first in Z modules and then include in real vector spaces. This is the multiplication of the real Clifford algebra with signature P and Q. So for 0, 2, this would be quaternions. For 1, 3, this would be the Dirac matrices. So these are kind of, well, if instead of having crossings here, I had a few braidings, I would actually have commutation relations instead of anti-commutation relations on the generators of this algebra. So this is a kind of sanity check on the idea of having both braiding and a crossing. So why would somebody have both? Why would somebody have both commutation and anti-commutation relations in an algebra?
Can I ask a question? I didn't really understand this picture here. You've got these grayed out things.
It's meant to mean that there's plenty of these. It's basically it's the usual thing you make to make the tensor product of two monoids, but with crossings instead of braidings. And the letter Q are also preceded by another crossing, which is the one which makes the square of a generator equal to -1 rather than 1.
With the fermionic.
Yes. So now we want to kind of break this molecule in its components. So actually add the binary leg gate as a generator. This, semantically, as I said, is interpreted as the Pauli X gate. This satisfies these two axioms. It is an involution, so this rule allows us to retrieve just the ternary black vertex from the previous generator. It also satisfies this funny rule. So now the crossing is not natural for everything anymore. So the black thing passes through the crossings, but a self-linking thing appears on the other strand. And if there is a topologist in the room which sees this and just says, oh, I recognize this, I would really like them to tell me at the end of the talk. So interesting thing is that with what we have so far, we only have purely even and purely odd maps. So this kind of calculus would also work for a kind of fermionic quantum computation like the one that Alessandro Tozzini was talking about yesterday. But to get all the maps, we need a kind of modicum of impurity, something which would bring us from purely even to purely odd into mixed things. And this happens to be exactly the GHZ node. Algebraic is a copy operation, so a copy operation is something which is impure quite clearly because it doubles everything, so it makes both even and odd things even. This satisfies, again, it is a monoid with itself with two inputs plugged together. It really works well as a copy for black things. It copies the black multiplication. It copies the black binary thingy. And there's also this kind of axiom, which is also a kind of, I don't have as good an interpretation of this as for the others, but it's again some kind of copying operation. So by plugging the multiplication in here, you get 2 units. And finally, the self-thinking is actually a phase for this gate, so it just commutes. And finally, there's this final rule, which it's used in completeness proof to eliminate a few of these crossings in favor of braidings. I also don't have a particularly good interpretation of this. I would be happy if it could be replaced with something more meaningful. So this is it. This is the axioms which are complete for the category which I mentioned. So what do I think would be the next thing to do? I guess it's pretty clear that my fixation about this is making things as topological as possible. I really think that string diagrams are really at their best when the qualities hold on the nodes, and there is a reason why after 10 years we're still kind of showing the teleportation equation to impress people. And so far I have a quite satisfactory understanding, purely topological understanding of this theory up to the second layer, so the one of even maps. I would like to extend that to further ones. And the other hope is that finding something like this would help us find better normal forms, because the completeness proof proceeds by normalizing diagrams to a normal form, but the current normal form is just, it's used to translate from vector notation to diagram notation, so it's kind of exactly as informative with regards to properties of entanglement as vector notation. One would want to go the other way around, so translate vectors into normal form diagrams, and then have some normalization which will disconnect everything that can be disconnected. And hopefully, like, if one has a kind of topological understanding, then things which are disconnected should be disconnected on the nodes. And finally, I think it's interesting to understand exactly how expressive each layer is. So I said that already with even maps at layer 2 we had the 2 3-qubit slot classes. Adding also this kind of odd operator, one could technically try to classify various topologies of entanglement for fermionic computation. And yeah, I think it's an interesting thing to study. Finally, there are the extensions. So far we have integers, and well, since we would want to normalize things in the end, having integers is kind of the same as having also rational numbers. But we might want to go into real numbers. I'm not sure how much this would change properties with regards to entanglement. One idea that one could have is make wires long something. So add a kind of signed metric. So far they're just topological objects without any notion of metric in them. But what I think would definitely change the entanglement properties, because complex Hilbert spaces and real Hilbert spaces are so different with regards to tomography, for instance, is adding some complex phases. And again, I hope that kind of topological understanding might help in this, because if one really takes seriously the kind of suggestion of flattened ribbons, this kind of self-loop on a ribbon is topologically equal to a double twist. So yeah, the fact that doing this twice gives you a trivial operation is basically the Dirac belt trick. So since one has a pi phase semantically modeled by a double twist, one idea is that having a single twist should be a pi over 2 phase. So since by now we're ready to see W calculus is strictly stronger than the CX calculus, only the real fragment of the CX calculus, the one which has only pi phases. Just adding this and being able to axiomatize it satisfactorily, it would lead to a calculus which is strictly stronger than the stabilizer ZX calculus. This is it. I will leave you with a picture of the normal form, which I want to explain now. You can look at it. Thank you.
Great, thank you. Amar. Any questions?
So like, in particular for 2x2 matrices with integer entries,
Yes.
you can write a normal form for them in this calculus.
Yeah, you can.
So like, if you look at the group SL2Z, right? So 2x2 matrices integer entries with determinant 1.
Yes.
That has like a known presentation in terms of these there's various presentations for it. How do those look like in terms of your calculus?
Oh, well, it depends. So this kind of if you write these matrices in this kind of back presentation by using match state duality, because then you can always bring things together. You get a normal form which looks like this. It's not always really informative. Usually there are some gates which looks like something in normal form but have a nicer presentation. For instance, the Hadamard gate looks pretty bad in normal form, but it can be described also as this thing, which looks quite nicer, I think. This should probably be more like the real normal form for which we are aiming, but that still has to be understood.
Is it easy to just say what the black dot is as a tripartite state?
The black dot, the ternary state, it is the W state. So it's the...
Yeah, but if you compose it with a poly on top, so you're just left with a single black dot, and then turn 2 wires up, you just write down the tripartite state codes.
so you mean just this one?
Yes.
Okay, yeah. This, well, there's no normalization here, so that it's